Have you ever stopped to think about the sounds you hear every single day? From the faintest whisper to the roar of a jet engine, there's this incredible hidden world of physics going on. So today, we're going to dive in and uncover what's really happening, from the whine of a passing siren all the way up to a mind-blowing sonic boom.
Let's kick things off with a sound that every single one of us knows. It's a simple, everyday mystery, but it's the key to unlocking the whole physics of sound. You know exactly what I'm talking about, right? An ambulance is coming at you, and that siren has this high, piercing pitch. But the second it passes you and starts moving away, the pitch just drops. It's the same siren making the same noise, but something about its movement is totally changing what we hear. So what is going on? And get this isn't just some weird trick our ears play on us. The very same physics that explains that siren's changing tune is exactly how a police radar gun clocks your speed. It's a really fundamental principle that has some seriously practical uses. Okay, so to solve this siren mystery, we've got to go back to square one and ask an even bigger question. What even is sound? It seems like a simple question, but the answer is the first big piece of our puzzle. Here's the key thing to get. Sound isn't some thing that's flying through the air. It's a vibration that travels through things. It's a disturbance that absolutely needs a medium, air, water, even a steel rail, to move. That's exactly why in the vacuum of space, it's totally silent. There's nothing for the sound to vibrate through. No air, no sound. And this is a perfect way to picture how that vibration works. Think about a speaker. As it pushes out, it squishes the air molecules together. That creates a little pocket of high pressure, which we call a compression. Then, as it pulls back, it leaves behind a space with fewer molecules, a pocket of low pressure, or rarefaction. Sound is just this repeating pattern of high and low pressure traveling from the source through the air and right into your eardrum. Okay, so sound is a pressure wave. Makes sense. The next question is obvious. How fast does it travel? You'd think that'd be a pretty straightforward thing to figure out, but it turns out this question actually stumped one of the greatest scientific minds in all of history. And here he is. Sir Isaac Newton took the first real crack at this puzzle. He came up with a formula using the air's pressure and its density. He crunched the numbers, and he got a very specific answer, 280 meters per second. A beautiful calculation from a brilliant mind. But it was wrong. Dead wrong. Because when other scientists actually went out and measured the speed of sound in the real world, the number they kept getting was this, closer to 332 meters per second. That's not a small error. It's off by about 16%. So what on earth did Newton miss? And this is what's so wild. Even Isaac Newton, the guy who gave us the laws of motion and gravity, was totally stumped. He knew his math wasn't matching reality, but he had no idea why. That puzzle, that error, just sat there, unsolved for more than 100 years. The hero of our story is a French mathematician, Pierre-Simon Laplace. He finally figured out the one thing Newton overlooked: heat. You see, Newton just assumed the air's temperature didn't change. But Laplace realized that as a sound wave squishes the air together in a compression, it actually heats it up just a tiny bit. And in the low-pressure parts, it cools it down. He added those tiny temperature changes to the formula and bam, 332.4 meters per second. A perfect match. Mystery solved. All right, so now we know what sound is and exactly how fast it moves. We have all the pieces we need to finally go back and crack the case of that passing siren. This whole phenomenon has a name, and it's called the Doppler effect. It was first thought of back in 1842 by its namesake, Christian Doppler. And then, just 3 years later, it was proven in one of the coolest experiments ever. A guy named Ballot literally put a bunch of trumpet players on a moving train and had musicians with perfect pitch stand by the tracks to listen as it flew by. See, science can be a lot of fun. So let's break down how this actually works. First, just imagine a sound source that's not moving at all. It's sending out those sound waves, those pressure waves, in perfect, even circles in all directions, just like the ripples you see when you drop a pebble into a still pond. But watch what happens the moment that source starts moving. It's literally chasing its own sound waves in the direction it's heading. You can see the waves in front of it start to get all bunched up and compressed together. Meanwhile, the waves it leaves behind get stretched out and pulled apart. And that's it. That's the whole secret right there. Your ear hears the frequency of these waves, how often those compressions hit your eardrum, as pitch. So when the siren is racing towards you, those bunched up waves are hitting you more often, and you hear a higher pitch. The moment it passes and moves away,
the stretched out waves are hitting you less often, and boom, you hear a lower pitch. It's so simple, but so brilliant. And this idea goes way beyond just sirens and trains. The applications are honestly incredible. Doctors use this exact same Doppler principle, but with ultrasound waves. They can bounce those waves off your red blood cells to see exactly how fast your blood is flowing. A change in that speed could mean a dangerous blockage, which makes this a tool that literally saves lives.
Okay, we've seen what happens when something moves through the air pretty fast, but what happens if it moves so fast that it actually catches up to its own sound? Well, this is where things get really, really dramatic. So imagine a jet. As it accelerates, getting closer and closer to that magic number, 332 meters per second, the sound waves it's creating out in front have less and less time to get out of the way. They just start piling up on top of each other, getting more and more compressed, until they form this massive wall of pressure. This is the infamous sound barrier. And then it punches through. The jet is now officially traveling faster than the sound it's making. It's outrunning its own noise. And all those overlapping sound waves it left behind form this V-shaped wake that trails behind the plane. We call this a Mach cone. That Mach cone is actually a continuous shock wave, a massive wave of built-up air pressure. Now, a lot of people think a sonic boom is a one-time thing that happens when you break the barrier, but it's not. It's what you hear on the ground when the edge of that continuous cone of pressure passes over you. That sudden, huge change in pressure hits your ears as one single explosive boom. So there you have it. We started this journey with a really simple question about a siren, and we ended up understanding how a jet can create this thunderous boom that can shake windows for miles. And it all comes back to that one core idea. Sound is just a physical vibration, a pressure wave moving through the stuff around us. And that kind of leaves us with one last thing to think about. We've been talking about sound moving through the air, but really, any object that's moving is creating pressure waves in whatever medium it's in, from a planet orbiting the sun to the blood cells moving in your own body. So if sound is really just a vibration, it kind of makes you wonder, right? What kind of unheard music is playing all around us, all the time, in everything that moves?